Hi everyone, welcome back. Today we're going to be talking about derivatives of logarithmic functions. In the previous sections we have worked with the derivatives of exponential functions, more precisely derivatives of e to the x. In the previous section, we also worked with logarithmic functions and their properties. And again, in this particular section, we are now going to be working with derivatives of logarithmic functions. So let's go ahead and let's start out with this concept or this example. I'm going to say here, let y equal to the natural log of x. And what I want to do at this point in time is I want to figure out how I'm going to take this derivative for this natural log function. One of the really nice aspects about this is that we know a lot about logarithmic functions. If we have a logarithmic function, then we must have an equivalent exponential expression. Well, it's our job then to find that equivalent exponential expression. So what I'm going to say is that at this point in time, now by definition, we get the equivalent exponential expression, which is e to the power of y equal to x. And again, this only works because we started off with y is equal to the natural log of x. Now, from this new equation, e to the y is equal to x, we can now start applying the derivative. And again, we're in the process of finding the derivative with respect to x. So that's where we go, is we go to consider the derivative with respect to x for e to the power of y. Now, what that means is, on the right-hand side, we need to also differentiate with respect to x. Now we're going to go through the whole process. The right-hand side is the easier one to tackle here. The derivative of x with respect to x, well, that's just derivative of x, which is 1. On the left-hand side, it's a little bit more complicated. We now get e to the power of y, take that derivative with respect to x. But if you remember back from section 6.1, when we were working with the derivatives of exponential functions, the derivative of e to the power of x is itself e to the power of x. If it's a derivative of e to the power of, let's say, u, where u is a function of x, then we must use the chain rule to find that derivative. And that's exactly what we're going to do here. Since y initially is a function of x, like we had at the very beginning, we get that when we take the derivative, it will be e to the y itself multiplied by the derivative with respect to x for my function y. In other words, multiplied by dy dx. So we're going to keep going. Now, at this point in time, if my left-hand side is now dy dx, then that means I can divide by e to the power of y. So if we divide by e to the power of y, we're now left with 1 divided by e to the power of y. However, at the end of the day, from the very beginning, we were given that y is equal to natural log of x. Which means when we try to find a derivative for y, we shouldn't have any y's left over. So if we make the substitution, or the resubstitution for what y is, we get 1 divided by e to the power of natural log of x. But if you remember from your natural log properties, e to the power of natural log of x evaluates to just be x. Which means we're really left with a simplified expression of 1 divided by x. And that's any time that I take the derivative of y with respect to x, and that's where y is equal to natural log of x. Well, what does that mean for us? What this means for us is that whenever we take a derivative with respect to x for a function that is the natural log of x, this derivative will then just be 1 divided by x. If we take the derivative with respect to x and there is a function composition, then we get 1 divided by u multiplied by du dx. And again, this is where u is equal to some function of x. Or we can take the derivative with respect to x for the natural log of some function g of x. If this is the case, again, we do the exact same process. Okay, that's going to be 1 divided by the function. So 1 divided by the function, we get the function in the denominator multiplied by the derivative of the inside function because of the chain rule. The derivative is g prime of x. So notice all of these three equations that I wrote on the right-hand side of the screen are all equivalent. And furthermore, we are going to make sure that we work with these equivalent expressions as we work through this particular section. So here goes your first example then, using this. We want to differentiate the following. And again, differentiating means that we need to take the derivative for the following. Part A. We are going to have f of x is equal to x times the natural log of x, and then we subtract x. So we need to find this derivative. Okay, here we go. What I'm going to do is I'm going to work step by step. Now, you're going to notice that as we keep working step by step, as the course progresses, some of those steps might get skipped as we move through the course because we are supposed to start picking up speed in taking derivatives and in integrating. So, here we go. Let's apply the derivative. So the derivative here, f prime of x, again, since my variable is x, I am differentiating with respect to x. So the right-hand side of my equation looks like this, where I have the derivative with respect to x of the function x times natural log of x minus x. And we keep going with the derivative properties, saying that we're going to need to differentiate the very first term, which is x times natural log of x, and then we're going to subtract out the derivative of the singular function x. Okay, that's not too bad. So let's keep going. Okay, differentiating the first part, this is going to lead us to the product rule. So the product rule for derivatives is what we need first. So now the product rule, we take the derivative of the first function. So the derivative of the first function, that's going to just be 1, multiplied by the second function, which is the natural log of x, plus the first function, multiplied by the derivative of the second function. There we are. That's my product rule. Now I still have to subtract out the derivative of x with respect to x, but that's just 1. Okay, not too bad. Let's keep going. Let's simplify if we can. Now, if you notice the second term, x times 1 over x, that's just 1, and 1 minus 1 will cancel itself out, which means we're only left with the natural log of x at the very end. And this is the derivative for that function. Awesome. It's looking good. Now again, when you're taking derivatives, please review your product rule, your quotient rule, and your chain rule from Calc 1. Again, they are going to be very, very beneficial for us as we progress throughout the semester. So let's go on to Part B. Part B, we have g of x, which is equal to natural log of sine squared of x. Okay. So there's what we have so far. Let's go through and let's start differentiating. Taking the derivative here, again, x is my variable, so I take my derivative with respect to that variable, and this is going to be the derivative with respect to x for the function natural log of sine squared of x as such. Okay, let's keep going. For that derivative, I am taking the derivative of the natural log, and again, I don't have anything added, subtracted, or being multiplied onto my natural log function. However, I do have a function embedded inside of it. In other words, I have function composition. And if you remember, anytime that you have function composition and you take the derivative, you must use the chain rule. So we're going to apply the chain rule, and it's actually the chain rule at the very top of your screen at this moment, the one that has the u embedded in it. If I take the derivative of a natural log function, then I automatically get the argument as the denominator. In other words, the argument is sine squared of x. So this is 1 over the sine squared of x, and now I need to multiply by the derivative of the inside, or the derivative of the argument. So what is the argument for the natural log? That's sine squared of x. Great. Now all I need to do is take the derivative of sine squared of x. So let's keep going. So the derivative of sine squared of x, so that's now going to be 2 times sine of x times cosine of x. Again, this uses a chain rule, and we must use that chain rule to work with this. Okay, there we are. Which now, once we are here, we can now multiply. Well, multiply and simplify. Notice there's a 2, so I'm going to carry that 2. So I get a 2, and then the signs cancel, and we're going to be left with 2 times cosine of x divided by sine of x. Now, cosine divided by sine, that is just cotangent of x. And here's your final answer. That says the derivative of your function g of x is 2 times cotangent of x. And there we are. Looking pretty good so far. Awesome. Now let's work with one more example. And that one last example is going to be part C, which is going to be y is equal to the natural log of cosecant of x minus cotangent of x. So here we go. We want to again take the derivative. So we're going to apply the derivative dy dx, because again the variable here is x, and that means I'm going to be taking the derivative of the right hand side with respect to the with respect to the variable x. Now you're going to notice that as we start this, the natural log function is the function that we're taking the derivative for. So that means that we then need to go ahead and take that derivative explicitly, but we are going to incorporate the chain rule. So here again we have dy dx is equal to, and this is going to be 1 over the argument of the natural log, which is just cosecant of x minus cotangent of x, and then this is going to be multiplied by the derivative of that argument. So the derivative of cosecant of x minus cotangent of x. So now we have to then start analyzing what is the derivative of cosecant x and what is the derivative of cotangent of x. Well, for that you can go back into Calc 1 and you can look up those derivatives that we need. So the derivatives here, the derivative of cosecant of x is going to get us negative cosecant x times cotangent of x, and I will put that here. There we are. The derivative of cotangent, so the derivative of cotangent, that's going to be minus. The derivative of cotangent is negative cosecant squared x. And that's for the second piece. All of this is still divided by cosecant of x minus cotangent of x. Now let's see if we can simplify some of these results. I see for my numerator that I can factor out a cosecant from my numerator, so I am going to go ahead and do that. So factoring out cosecant, there we are, is now going to get me negative cotangent of x plus cosecant of x, all divided by cosecant of x minus cotangent of x. And if you analyze this just a little bit further, you will see that the factor in the numerator is the same as the whole denominator. Since that is the case, those factors will cancel, and all we have left with at the end is that the derivative of that function with respect to x is equal to cosecant of x. Check that out. That is awesome. Awesome. So again, this is what we now are starting to analyze, is what are the derivative of these natural log functions that we have now come to know and have come to work with. Now we're starting to apply calculus to this. Okay, so let's keep working a little bit more, and let's keep on extracting what we know, since we already know this process. So here's what I want you then to look at. Okay, so let's go ahead and let's start looking at this function. Let's look at the function of the natural log of the absolute value of x. This is a pretty nice, interesting function. And what I want to do with this function here we go. What I want to do with this function here is I'm going to call this function f of x. And I want to know more about this function. Okay, so since we have an absolute value, that means that the absolute value actually breaks this function into two different parts. In other words, it's a piecewise defined function. That piecewise defined function now says that I can take the natural log of x, and this only evaluates, and that's going to be if x is greater than 0. Okay, so that's kind of nice for what we're looking at. Well, what about the negative portion? Well, if we ever choose a negative portion here, or a negative value, then that means we're going to be evaluating with natural log of negative x. And again, this only if x is less than 0. Notice I'm not equaling 0 at any one of these pieces because the natural log of 0 does not exist. If you remember, we have an asymptote at that point. Okay, so now I'm looking at this. Now I can go through and I can say, okay, but well, back from Calc 1, I couldn't take the derivative of piecewise functions as is. However, if I broke them down into each individual piece, then I can go ahead and start taking that derivative to see what we get. Okay, so let's start considering that now. Let's take that derivative. So the natural log, I'm going to take the derivative of the natural log of x. So that means I'm applying this derivative. So we're applying the derivative for the natural log of the absolute value of x. And what are we getting here? Well, for the piecewise defined function for the first piece, the derivative of natural log of x, well, that's actually nice. It's just 1 over x. And this is going to be, again, if x is greater than 0. Well, now the natural log of negative x, well, this then occurs. So let's go ahead and take the derivative. That's going to be 1 over negative x multiplied by the derivative of the inside. The derivative of the inside, that's negative 1. And again, this was if x was less than 0. But check that out. That now simplifies. So this now simplifies 1 over x if x is greater than 0. And we still get 1 over x if x is less than 0. Wow, that's pretty cool. So this now condenses to the exact same function. Look at that. It's no longer pieces. Well, technically, it's still 2 pieces. We'll get around that in a little bit. However, it's the same function for the 2 pieces. Doesn't matter if we have positive x values or negative x values, this derivative is still going to evaluate as 1 over x. Which means this derivative here is now just the derivative for my natural log of x. In other words, it's f prime, which is just 1 over x, provided that x is not 0. And that's the way we get around it. So what's really, really nice about this is that we get this key aspect. And this key aspect that we get is that whenever we take the derivative of the natural log of the absolute value of x, we naturally just get 1 over x itself. Awesome. Now, that plays out on a grander scale, but I want you to then consider what we were looking at up here. Considering what we were looking at up here, the function that we started with, the function that we started with was just the natural log of x. It was only the first assumption on this piecewise function that we worked on. However, there was a second piece, and that second piece said that any time that we're working with that absolute value of x as the argument, then its derivative is always 1 over x for that natural log. Now, why am I babbling on about that? Well, there's one specific reason. The one specific reason is that I now want to use the antiderivative. In other words, I want to apply the fundamental theorem of calculus here. Well, let's go through and let's figure out how we're going to do that. So, we're going to say applying the antiderivative, or applying the integral, so if we apply the integral, we now get that the integral of the derivative with respect to x for natural log of the absolute value of x and this is all dx, is equal to the integral of 1 over x dx. And again, using both sides as that, applying the integral to both sides. And now on the left-hand side, by the fundamental theorem of calculus, on the left side, we are now left with the natural log of the absolute value of x. On the right-hand side, we're left at the integral of 1 over x dx is equal to this piece. But now that's kind of interesting because it is now at this point in time that we now get to see that when we take the antiderivative of 1 over x, it's not just going to be the natural log of x as we would have initially thought from the very beginning when we started this. Because looking at that antiderivative from the very first work that we did, we would naturally say, hey, it's the natural log of x. However, being a little bit more precise, we now say that the integral, or the antiderivative for 1 over x, is the absolute value of x embedded inside of the natural logarithm. Or in other words, the natural log of the absolute value of x. And this is where our rule comes into play. We're going to look at evaluating integrals of the form 1 over x. When this happens, we need to make sure that we always interpret the natural log of the absolute value of x plus c. All right. So this is what we're doing for this particular process when we need to evaluate these integrals. So let's go through and let's start evaluating these. So evaluate the integral. Part A. We're going to go with the integral from 0 to 3. So again, we're getting a definite integral, and this is going to be dx over 5x plus 1. Okay, so now we're starting to get into the integration portion for these antiderivatives of exponentials. So let's go ahead and we're going to write out all the steps at the beginning, and then we're slowly going to start cutting out some of the steps as we proceed throughout the semester or these lessons. Okay, so one of the items that I see first here is that I have a denominator of 5x plus 1, so I want to make a substitution. And this is my substitution, that u is equal to 5x plus 1. So if u is equal to 5x plus 1, then that means du is just going to be 5x dx. Furthermore, x dx is just 1/5 du. Well, what that tells me here for this integral now, it tells me that I now have the integral, my dx portion, I said x dx. Wow, that's pretty bad calculus for me. My apologies. There we are. Just like that. U is equal to 5x plus 1, so the derivative is just du is equal to 5 dx. Divide by 5, and we get 1/5 du is equal to dx. Therefore, when I make my substitution, my dx just becomes 1/5 du. So that's 1/5 du divided by my denominator, which was u, that 5x plus 1. Now I'm going to re-index, or in other words, I'm going to change my limits of integration. So changing my limits of integration, sorry, I'm fixing that numerator. There we are. So now fixing my limits of integration, or let's say changing my limits of integration, I'm now going to look at my first top number, which is x is equal to 3. Well, if x is equal to 3, so x is equal to 3, I'm now going to use this equation here to say that u is equal to 5 times 3 plus 1, which means that u is equal to 16. There we are. Lower limit of integration, x is equal to 0. So if x is equal to 0, I now get that u is equal to 5 times 0 plus 1, which means u is equal to 1. And there's my lower limit of integration. Using my calculus or my integral properties, 1/5 is a constant. So I factor that constant out of the integral, and I'm left with the integral from 1 to 16, evaluated for 1 over u du. Now I can go through the process and integrate 1 over u. Well, the integral of 1 over u, that's going to be the natural log of the absolute value of u, and that's going to be evaluated from 1 to 16. Let's keep evaluating here. That's going to be the natural log of the absolute value of 16 minus natural log of the absolute value of 1. Natural log of 1, that's just 0. Natural log of 16, absolute value of 16 is just 16, which means we're left with natural log of 16 divided by 5. Or you can say natural log of 16 to the power of 5. Whichever one of these answers is completely correct. And that is the first example, part A. Part B, we're going to work with something similar. So here's the example where we have the integral of cosine of the natural log of t divided by t, and this is going to be with respect to t. Now again, we have a few options that we can take here. Because I see function composition, and the function composition is occurring where we have cosine of the natural log of t. And using that function composition, I am going to make my substitution where I will say that u is equal to the natural log of t. Therefore, when I take du, I now look at du in this form of 1 over t dt, because again I took the derivative of natural log of t. And if you notice, 1 over t actually does show up in the integrand, so that's 1 over t dt. This now looks like the integral, the integral for cosine of my substitution, that was u, and then 1 over t dt, 1 over t dt becomes it just becomes du. So here we are, just as such. Now, what we do here is we just find the antiderivative for cosine. So finding that antiderivative, or as we call it, the integral for cosine of u, well, that integral then turns out to just be sine of u plus c. And again, we need that plus c because we need that constant of integration, because this is an indefinite integral, whereas the example before this was a definite integral because we were given those limits of integration. Now let's keep going. So at the end of the day, because this is an indefinite integral, I need to substitute my u back into my function. So here it goes. So now this is sine of u in this case, which was the natural log of t, and then plus c. And that's my final answer. Nothing more, nothing less. That's it. That was part B. Let's look at part C. Part C is going to be the integral of e to the power of x divided by e to the power of x plus 1, and this is all with respect to dx. Okay, so again, what I see here is I see some function composition where I can take the denominator here and make the substitution that I'm looking for. So in this particular case, I am going to say that u is equal to e to the x plus 1, because when I look at the derivative for this function, for that substitution, I'm left with du is equal to du is equal to e to the power of x dx, which again tells me that e to the x dx, here found in my numerator, or in that integrand, I'm able to make that substitution. So now this is an indefinite integral. My substitution is e to the x dx, that's now going to be u, and the denominator here is going to be u. So this integral now turns into 1 over u du. And if this is the case, then I can go through and evaluate this. This will now be the natural log of the absolute value of u plus c. And because it's an indefinite integral and I need to solve, or I need to find the derivative, that means I need to input my initial substitution, which was e to the x plus 1 inside of my natural log plus c. Now you're going to notice that every time that we make that substitution back in, that back substitution, what we have to do is we then always have to analyze that result, the argument that we're inputting into that absolute value. Is that absolute value, is that expression in the absolute value always positive or sometimes positive? Well, in this particular case, e to the x plus 1 is always positive, which means we can drop the absolute value and it will be the natural log of e to the power of x plus 1 and then plus c. This is my final result. This is the final result, part C. Great. Now let's look at one more. And this is going to be part D. Part D, we want to evaluate the tangent of x dx. Now notice, back in Calc 1, you did the derivatives of the trigonometric functions. However, we didn't visit the antiderivative for tangent of x, at least not in Calc 1. And the reason for that is because we still need we still needed a little bit more material, and that material is the natural log derivative, or in this case, the natural log antiderivative. So now that we are here, let's go through and let's see if we can try to extract what this is going to be. Okay, so for the first part, what I am going to do is I am going to rewrite tangent in terms of its quotient, which is sine of x divided by cosine of x dx. And then I'm going to make a substitution that the denominator is cosine of x, that's u. Well, if that's the case, then what's going to happen here is that when I take the derivative, I get negative sine of x. And that is where we want to be, specifically because at this point in time, we could now go through our integrand and make that resubstitution, or make that substitution. Sine of x dx, that's sine of x, oopsie, here we go, that's sine of x dx, that's going to be negative du, so that's going to be negative du, and then we have 1 over cosine, which is u, so this was 1 over, or negative du, as such. Negative can factor, and we're left with 1 over u du, exactly as is. Okay, so finishing this off here, we now get to see that this integral is now negative of natural log of the absolute value of u, and then we still get a constant here because it's an indefinite integral. But then again, at the end of the day, we want to evaluate that absolute value here, or that u value. So this is going to be negative natural log of the absolute value of cosine of x plus c. Now again, this is where we need to be very, very careful here. We cannot drop the absolute value because cosine does have negative outputs. Alright, so we do have to leave the absolute value there because cosine is not positive for all values. So be very, very careful with that. However, what we can do is we can apply this -1 to the argument. Because we have a negative multiplied the logarithm, -1 was multiplying, therefore we can raise the argument to that power, and cosine of x to the power of -1, that is the inverse of cosine. The inverse of cosine is secant, which means this is really the natural log of the absolute value of secant of x plus c. And this is a very important integral because you will be using this not only in this course, but in future courses as well. So this is a super uber important result. And I'm putting little red asterisks next to it because, again, we need to make sure that we know how to do this moving forward. Okay, in this class, I might ask you to perform this on an exam or on a quiz. In your next class, in 5C or multivariable, wherever it is that you take it, you could be asked to just use the result of this, meaning you have to know what the integral of tangent of x dx is. All right, so let's keep going then. What we want to do now is we want to talk about differentiating a logarithm that doesn't have a natural base. So in other words, a logarithm that has any other base besides e. So what we want to work on here is we want to work on differentiating logarithm base b of x. So this is what we want to work on. Now, the nice part about this is that we are going to rely on methods that we already know how to integrate with. So in order to do this, what I am going to want to do is apply the derivative, but only apply to the derivative to the change of base that I'm going to be able to extract. So here, when I take the derivative with respect to x, and this is going to be for log base b of x, well, the argument, or sorry, the function logarithm base b of x actually turns into a change of base if we use natural log of x divided by natural log of b. And that's exactly what I want to use here. Again, this was a change of base. And I do believe we mentioned the change of base back in section 6.1. So if you're having trouble recalling what that is, you can go back to that section and you can check it out there. So at this point in time, taking the derivative with respect to x, check this out. The denominator is a constant. Natural log of b, where b is any real number that we, or sorry, any acceptable base real number, then that means the natural log of b in that denominator is now a constant. So what do constants do inside of derivatives? Well, they factor. Which means we're taking the derivative only of the natural log of x, and we're dividing by the natural log of the initial base. But what's the derivative of natural log? Well, the derivative of natural log is just 1 over x. Which means at the end of the day, my answer is 1 over x times the natural log of b. That is the final result. And that is one of the results that we need. So we're going to kind of keep this in our back pocket saying, hey, this is something that I need because it is something beneficial that we will be using later. Awesome. So that was one of the first ones. Now let's look at a different one. Okay, so let's work with the other one. We want to now differentiate b to the power of x. And now when we start looking at b to the power of x, we want to find that derivative. So in the grand scheme of things, I want to find what is the derivative with respect to x for the function b to the power of x. Now that one might be a little bit tricky, so let's go ahead and let's start breaking it down step by step. Okay, so what I want to do first in this particular case is I want to use this piece of information that I have y is equal to b to the power of x. And if this is the case, then naturally I am able to extract some form of a natural log here. Because again, we have an exponential, therefore we must have a logarithm as well as an equivalent form. What is that equivalent form? Well, that equivalent form, if I take the natural log of both sides, will then be natural log of y is equal to the natural log of b to the power of x. But natural log of b to the power of x, since this has an exponent in the argument, this could be rewritten as x times natural log of b. Now that's pretty nice because what we get to do now is once we have this, then we can get rid of the natural log of y on the left-hand side. We get rid of it by raising both sides to the power of e. So we do e to the power of natural log of y and e to the power of x times natural log of b as such. What happens here? Well, on the left-hand side, we're left with y. On the right-hand side, we're now left with e to the power of x times the natural log of b. So I want you to then check this out. Oops. We have two versions of y. Y is equal to b to the power of x, and y is also equal to e to the power of x times natural log of b, which means they are both equivalent forms. So if they're both equivalent forms, when I'm taking my initial derivative, right here in the top row where I started, b to the power of x can now be expressed as e to the power of x multiplied by the natural log of b, all in that exponent. That is great. And I say that is great because we now get to take the derivative of an exponential function. More importantly, the derivative of a natural base. So when we take the derivative of the natural base, we get the function itself back, which is e to the power of x times natural log of b. However, we also get to multiply by the derivative of the inside of the function, or in other words, that function composition. So the derivative of x times natural log of b. But what's the derivative of x times natural log of b? X is the only variable, which means natural log of b is a constant, so the derivative of the variable x is just 1, which means it's 1 times natural log of b. So here we just get the natural log of b multiplied by e to the power of x times the natural log of b. But at the end of the day, once again, what is this expression equal to? E to the power of x times natural log of b? Well, that was my initial b to the x, which means that at the end of the day, I'm left with natural log of b multiplied by b to the power of x. And this is my derivative for any base to the power of x. So again, we operated, or we use the operation on these two processes. Okay, now I am going to summarize those on the right-hand side of the screen. And that summary is going to say that when we look at the derivative of the natural log of x, the derivative with respect to x for logarithm base b of x, then that's going to get us 1 over x times natural log of b, natural log of the base. What does it mean when we then take a derivative with respect to x for b to the power of x, where b is any base other than e, because e would be a nice one. So this derivative then gets us b to the power of x multiplied by the natural log of b. And very similarly, we can go with the extraction as well, that when we start looking at the antiderivative for b to the power of x, the antiderivative for b to the power of x is going to be b to the power of x divided by natural log of b plus c. Awesome. So there are our derivative rules, or these derivative properties that we want to work with more explicitly. And those properties are on the right-hand side. And again, those are the properties that we want to work with. So let's keep going and let's start applying those properties. So here goes our first example. Differentiate the following. Part A. We want to differentiate y is equal to log base 2 of x times, that was x times log base 5 of x. So that's the one that we want to differentiate first. Alright, so let's give this a shot. We want to take the derivative here, so the derivative is going to be with respect to x, and this is going to be d dx for the function of log base 2 of x times log base 5 of x. Okay, so the first thing I am looking at is that I'm initially taking the derivative of the outermost function, which is logarithm base 2. Now, because it's a derivative of a logarithm with a base, I know that I'm going to have to use one of my properties here, and that's going to be the very first property that I outlined just a little while ago. Which means that when I take the derivative of this natural log, what I am going to get here is going to be, this is equal to 1 divided by the argument, and that argument is x times logarithm base 5 of x, as such, multiplied by the natural log of the base of the logarithm, which I just took the derivative for, and that was 2. There we are. Okay, looking pretty good so far. Now I'm going to keep going. So, at this point in time, again, I had 1 over the argument multiplied by natural log of base. Then I still need to take the derivative using the chain rule, derivative of the inside. So the derivative of the inside, that's going to be the derivative of x times log base 5 of x. So what does this derivative look like? Well, in order to take that derivative, we need our product rule. So we're going to use a product rule here. So I'm going to write this out that this needs a product rule. And again, this is only going to be that numerator. Derivative of the first, which is 1, so that's going to be log 5 of x, log base 5 of x, plus the first derivative, which is, the first function, which is x, multiplied by the derivative of the second function, and that's going to be 1 over x times natural log of 5. And this is all divided by x times log base 5 of x times natural log of 2. Awesome. Everything's looking pretty good so far. Now, the reason I say everything's looking pretty good so far is simply because I can now start simplifying just a little bit more. One of the things that I want to do here is this logarithm base 5 of x. I'm going to rewrite logarithm base 5 of x in terms of its change of base. Notice the second term for that numerator, x divided by x, just leaves us with the denominator of the natural log of 5 divided by x times natural log of x divided by natural log of 5 multiplied by the natural log of 2. Notice every single term in the numerator and denominator has a factor of natural log of 5, which means that if we then multiply by the natural log of 5, both numerator and denominator, they will cancel, which will then leave us with a numerator of the natural log of x plus 1 and a denominator of x times natural log of x times the natural log of 2. And that's the final result. This is the derivative that I am looking for. There we are. So this is how these derivatives are working, and this is how we're going to want to keep working with them. Every time that we identify a product rule, we have to then go ahead and use that product rule. Chain rule, quotient rule, whatever that may be, we have to apply it. Part B. Let's work with the function capital F of t is equal to 3 to the power of cosine of 2t. Okay, so again, what I'm noticing here is that my variable is in the exponent, and since my variable is in the exponent, I know I'm going to have to use some type of exponential derivative. The ones that we stated before, the two properties, as you see on the top of your screen, I'm going to be using the second property, which means I'm going to be taking the derivative of a base raised to some power. So when I do this, when I start taking this derivative, f prime of t, this is going to be the derivative with respect to t, and this is going to be for 3 to the power of cosine of 2t. Okay, so taking the derivative here, I'm going to be left with the base and the derivative itself. So the base in that derivative, so here I'm going to be left with 3 to the power of cosine of 2t, and then this is going to be multiplied by natural log of the base, which was 3, and then multiplied by the derivative of the exponent, because we have a chain rule. Okay, so let's keep going. 3 to the power of cosine of 2t multiplied by natural log of 3 multiplied by the derivative of cosine 2t, well, the derivative of cosine of 2t is going to be negative 2 sine of 2t. And once I put everything together, I get negative 2 sine of 2t multiplied by natural log of 3 multiplied by 3 to the power of cosine of 2t. And this is a derivative for that function. There we are. And that's all there is to it there. That looks really, really, really great. Awesome. All right, so now let's start extracting a little bit more. Okay, so one of the questions now that we want to focus on is how do we differentiate this function here where we have y is equal to x to the power of x. Notice we have x to the power of x, so one of the things that we can look at is possibly a power rule, but then power rule only works when your variable is a constant, not an exponent. And so then we can say, well, maybe we can use an exponential differentiation, but exponential differentiation only works when your base is a coefficient or a constant. And in this case, both the base and the exponent are variables, which are going to be kind of, let's say, difficult to work with. So instead, what we try to use here is we try to use our algebra techniques to break this down a little bit further. What we can do here is we can apply the logarithm function onto both sides. In doing so, we now get that the natural log of y is equal to x times the natural log of x. And this we can take the derivative for. So if we then apply the derivative here, so let's say d dx of the natural log of y, and on the right hand side we do the same thing, d dx of x times the natural log of x. Then on the left hand side, the derivative for the natural log of y, that's going to be 1 over y multiplied by dy dx, again that chain rule. On the right hand side, it's derivative of the first, so that's going to be 1 multiplied by the natural log of x, which is the second function. Then we take x and multiply by the derivative of the natural log of x, which will just get us 1, and this is by the product rule. Then again, if we were in the process of finding the derivative for y prime, check this out. dy dx is equal to y times natural log of x plus 1. And this is simply because I multiplied the previous equation by y on both sides. Well, then again, what is y? Well, y, according to the very beginning, is x to the power of x multiplied by natural log of x plus 1. And guess what we just found? That's the derivative. So what this process is called here, this process is called logarithmic differentiation. And logarithmic differentiation basically tells us that as long as we're using the chain rule, and as long as we are using this explicitly, or in this case implicitly, then applying implicit differentiation to these logarithmic functions, we can find these derivatives and we can simplify these derivatives to make them nice. So that is what we're working with for one of the last portions of this section, is we are using logarithmic differentiation. So on this first example, or on this example, we're going to use logarithmic differentiation to find the derivative. Okay, so part A. So in order to work with part A for this one, we're going to be given y as e to the power of negative x multiplied by cosine squared of x divided by x squared plus x plus 1. Okay, and now we want to go with that, again, logarithmic differentiation. So let's go through with this here. We're going to be looking at our y prime. So in order to do that, what I'm going to do is I'm going to apply the logarithm function to this, or the logarithms to this function. So let's start off. Logarithm of y is equal to logarithm of e to the negative x times cosine squared of x divided by x squared plus x plus 1. Remember, with logarithms, anything that's multiplying inside of the logarithm gets split with addition. So plus the natural log of cosine squared of x. Anything that's being divided can be split into subtraction of the logarithms. And this is logarithm of x squared plus x plus 1. As such. Now I can go through and I can then start taking this derivative, because again, this derivative is going to be a little bit easier to work with. Let's see how in that case it's going to be easier. Okay, so here we go. Let's simplify this just a little bit more. Natural log of y. I'm going to simplify the first one here. This is going to be negative x times natural log of e, as such, plus 2 times natural log of cosine of x, minus, and then we can't do anything there, so that's going to be minus natural log of x squared plus x plus 1. Now we can apply the derivative to both sides. So applying the derivative to both sides, natural log of y, that's then going to be 1 over y, multiplied by the derivative of y, which is dy dx. On the right-hand side, look at the first term. Natural log of e, well, natural log of e, that's just 1, which means the derivative of negative x is just negative 1. Okay, not too bad. Let's keep going. So the next part, taking the derivative of natural log of cosine. So 2 is a constant, so that stays out. So natural log of cosine, that's going to be 1 over its argument, cosine of x, multiplied by the derivative of the inside, which is sine of x, minus this argument in the denominator, that's x squared plus x plus 1, and that's going to be then multiplied by its derivative, which is 2x plus 1. Okay, it's looking good so far. Now all we have to do then is multiply by y, which means the derivative here, dy dx, once we multiply by y, it's going to be y times the quantity of negative 1 plus 2 tangent of x minus 2x plus 1 divided by x squared plus x plus 1. And our final item is to insert what y is. So we already know what y is. Y was given to us at the very beginning. So we know that this dy dx needs to be e to the power of negative x times cosine squared of x, divided by x squared plus x plus 1 multiplied by negative 1 plus 2 tangent of x minus 2x plus 1 all divided by x squared plus x plus 1. And there we are. There's our derivative. That's our final answer. Isn't that awesome? That is beautiful. Great. So that is logarithmic differentiation. And again, we have to get good with logarithmic differentiation because, again, at the end of the day, logarithmic differentiation is simply just using implicit differentiation where we have logarithms now to worry about. Okay, so let's go with part B. So here we go, part B. We want to use, or we want to differentiate y is equal to sine of x raised to the power of natural log of x. And we're going to do the exact same process here. Since we now have to take a derivative and we have this argument, we have this exponent and this base that both have variables, then what we want to do is we want to use logarithms to break this down. So apply the logarithm, that's going to be logarithm of y, is equal to, in this particular case, logarithm of sine of x raised to the power of natural log of x. I'm going to use my properties of logarithms to break this down. So this is going to be natural log of x multiplied by natural log of sine of x. Awesome. So it's within this function now, within the natural log of y, that I can now start taking these derivatives. Okay, so let's apply the derivative. Applying the derivative on the left-hand side will leave us with 1 over y multiplied by y prime. In other words, 1 over y multiplied by the derivative of y. On the right-hand side, we need a product rule. The product rule will then say take the derivative of the first, so that's 1 over x, multiply that by natural log of sine of x, plus take the first function, natural log of x, multiply by the derivative of the second function. The derivative of the second function is 1 over sine of x multiplied by the derivative of the inside, which is cosine of x. So now what I'm going to do is I'm going to multiply y onto both sides. So multiplying y onto both sides, and now that means I'm left with 1 over x multiplied by natural log of sine of x plus natural log of x multiplied by cotangent of x. As such. Okay, that's looking pretty good, but now what is y? Well, y from the very beginning, that's what was given to us. Y is the sine of x raised to the power of natural log of x, and now that y is being multiplied by this whole parenthesis, 1 over x multiplied by natural log of sine of x plus natural log of x times cotangent of x. And this is your final answer. Again, when we're doing these derivatives, we have to remember all those properties, and we have to know how to extract all of those different values for those different properties. Awesome. Awesome, awesome, awesome. So let's go ahead and let's work on one last example, one last item, one last topic here, and then we can wrap up this section. Okay, so let's view this one really nice concept. I'm going to begin with a function here, which is natural log of x. And what I'm going to do here is I'm going to consider its derivative. F prime of x is simply just 1 over x. Now, when I take this f prime of x and I evaluate f prime of x at 1, we know that we will naturally just get 1, because inserting 1 into that derivative automatically gets us 1. Okay, awesome. So we know that. Next, what I want to do is I want to now use the limit definition. So using the limit definition here, I'm going to be looking at the limit as h is approaching 0, and this is going to be for x plus h minus f of x, all divided by h. And so we're going to go through the whole process, and we're going to start figuring out what these values are. Okay, so using this, what I'm going to want to do here is I'm going to want to now say that I want to evaluate x being at 1. So if x is 1, then we're still going to need to go through this exact same process. Limit as h is approaching 0, and this is going to be for f of 1 plus h minus f of 1, all divided by h. Alright, looking pretty good so far. So we're going to keep going. Natural log as h is approaching 0 for the function of 1 plus h raised to the power of, in this case it's f of 1, but the function is natural log, so actually I want to rewrite the natural log back in. So the first one is natural log of 1 plus h minus the second function is just the natural log of 1, all divided by h. Natural log of 1, that's just 0, which means this function here turns into the limit as h is approaching 0 for 1 over h times the natural log of 1 plus h. That's pretty cool so far, but more importantly, this is a limit as h is approaching 0 for natural log of 1 plus h raised to the power of 1 over h. Because again, anytime that a coefficient is multiplying the logarithmic function, it can be thought of as the exponent of that base. Now, when I take this limit, or how I take this limit, I now get to view the different types of processes that I can extract. And more importantly, the process that was developed back in Calc 1, which talks about the derivative, or in this case, the limit of exponential or function compositions. Alright, so this is real nice because again, this is equal to f prime at 1. So if we follow all this along, we actually get that 1 is equal to, in this particular case, the limit as h is approaching 0 for natural log of 1 plus 1 over h to the power of 1 over h. Now check this out. So I want to modify this just a little bit. Okay, so let's modify this. Let's say it's e to the power of 1. Okay, well we know e to the power of 1 is just e itself, where in this particular case 1 is going to be this limit. So 1 is this limit as it's approaching natural log of 1 plus 1 over h to the power of 1 over h. So check that out. That in itself is amazing. Now what will happen here is that the limit will actually move through the function composition here because of what we learned back in Calc 1. Which means this is going to be the limit, excuse me here, this is going to be e to the power of natural log of the limit as h is approaching 0 for 1 plus 1 over h to the power of 1 over h. And this particular piece in here, e to the power of natural log, well, e and the natural log, they're inverse functions of one another, which means this really just comes out to be the natural log, or limit, of, in this particular case, 1 plus, oops, excuse me here, 1 plus 1 over h to the power of 1 over h. So this tells us that e can actually be expressed as a limit. Now, if we replace h's with x's, then we naturally get this expression. Now, this is really, really highly interesting because at the end of the day, your constant for e is now expressed as a limit of a function. We're going to investigate those types of limits more at the later part of chapter 6. So stay tuned for that, but at the end of the day, this is it. This is what we are looking at when we're talking about derivatives of logarithmic and these exponential functions. So I hope that you all enjoyed this lesson, and I will see you all for the next one.